Good morning. I hope that you're doing well. I'm doing very well, as you can probably guess from the thumbnail of this video. Things have gone surprisingly well in this last week. And although last stream I said that I was going to try to approach Ball Butler stuff in a bit more of a sustainable manner for the next couple of weeks, that didn't really happen this week. I couldn't help myself, and I've done a lot of stuff and put in a lot more hours into this than I was kind of expecting to, but I have no regrets at all. It's coming along very, very nicely, and as you can probably imagine, I'm very eager to show you what I've been up to. So let's get into it. I did not update my little subtitle this time because I forgot. As always, it's a bit of a mad rush before the stream starts, but everything else is in there, so it's not too bad. Okay, so before I show you the cool things, which we'll get to very shortly, I've deliberately not delayed them as long as I normally do. The demos, that is. Well, singular demo. I just wanted to cover some stuff from last week. There were some ongoing problems that I showed off in the stream last week where I didn't really have any known, like I had no idea what the problems were basically and had no clue what the solution might be, and I want to just go through those before showing you the demo. So, the first problem that I was facing last week is getting the ODrive micros working. So, normally, in the past when I have been using brushless DC motors, I've been using ODrive Pros because that's just what I bought the first time that I made an order from ODrive. And these have been very good. They have, they do everything that I want them to do, and it's usually not too tricky to get working. But for Ball Butler, I want to use the smaller ODrive Micro, which is quite a bit smaller than the ODrive Pro. And I've been having last week I was having issues with getting these to work with my motors. So, let's see what... my thinking process was that maybe... Well, I had a couple different steps that I could have taken to diagnose this, and I did end up going through a couple, but my first thought was that maybe I should try a higher voltage, because right now, Ball Butler, I would lift it up and show you, but it's all connected. You'll see in a sec. But Ball Butler now is... I'm planning on it being run off of just 12 volts, and that is at the very low end of what the ODrive Micro is quoted for. And also my motor, I don't know how happy my motors are being run at such a low voltage, so I figured maybe I should just try bumping up the voltage and then see if that makes the problems go away. Maybe, I figured at a minimum, adding more voltage would allow the ODrive to put out a bit more power and to potentially overcome. It felt like last week some of the problems were related to there not being enough torque in the motors, and it's just not able to overcome friction in the motor to start spinning. So I was thinking maybe adding more voltage would allow for more power, would allow to overcome whatever friction we have. Maybe, was my thinking. So I was like, okay, cool, maybe I can try high voltage. But I pretty quickly realized a big problem, which is that I can't easily get in to access the Teensy. And to explain why this is an issue, I want to show you... let's have a look at this. I've got some other CAD that I want to show later, so try not to give yourself spoilers. But basically, inside the box here, you may remember that we have... Actually, I'll just look at just the base. What? Why did that not open? Yep, so inside the base, we have, if it will load, a bunch of electronics, and come on. And basically in here, we're powering a Teensy, which needs to be run off of 5 volts, and we have 12 volts coming in. So I have a converter. What is going on? Where's my model? All right, I guess we'll do it on here. We've got 12 volts coming in through this connector over here, and that runs through and goes into the Teensy. We have this little buck converter in here, to convert that into 5 volts to power the Teensy. Now, it does turn out that this buck converter, I'm fairly sure, is happy with any input voltage up to 20 volts, so I could have actually done the testing that I wanted to do with this, but I really don't want to break my Teensy, so what I was planning on doing is, if I could get access onto the inside, then I would take out the Teensy, just the single Teensy chip, and then that way the power will just run through. And because I've got the bus bar set up, which I don't have in CAD, but I showed in the images last week, and there'll also be an image of this in the stream later. Because of the power routing bus bar situation that I've got, I can very easily just remove power from the Teensy control chip and then still have that power run through to the ODrives. So I was hoping that if I could get access to this, I could remove the Teensy and all its power connectors, and then power the 2 ODrives off of 24 volts, and then see if that works. Now, of course, that still involves both of these ODrives being like in situ, so like they were already strung up, so they're like connected to their axes, which means I would have had a lot more limited range of motion than if I just had them free. Like, for example, what I ended up doing was to basically separate. Whoops. That was straight on the macro pad. I have enough of these motors, thankfully, to be able to connect them basically on like a standalone thing. So I could have just the motor and just the ODrive, and that way I could test this in isolation by itself, which is very nice to do, because when you're first setting up these motors, it's not hard to have them accidentally, like just one little keystroke difference, you put the decimal in the wrong spot, all of a sudden your motor's flying away. And if it's rigged up in your actual system, it's pretty easy to break stuff. So having it like isolated like this was very, very, very helpful, and allowed me to realize what the actual problem was. But I'm getting ahead of myself. So let's go back to the slides. Yes, so I can't easily get into access the Teensy, which is a bit of an oversight with this design. Like once this has been connected up, it's very hard to unconnect. And by the way, the reason why it's hard to disconnect is because inside here, we have this blue cylinder is a slip ring. So there's cables that come out of the slip ring and come through this little channel in here, go up into the slip ring. The outer part of the slip ring stays still, but then there's an inner section, this guy here, that can spin. And everything is blocking it right now. Let's see. Nope. Yes, we have this CAD open now. Great. So this little middle part spins, and these cables come up through there. Now those cables that come up through the spinning section come up through this big main ring part, through this channel in here, and then they go up and around. And yeah, if you want more details on that, check out the stream last week. I showed it off in a bit more detail. Yeah, but the problem is that if I try to lift up this lid that the big ring is connected onto, then that means that the cables that come out of the slip ring need to, either the cables on this end or the cables down on the bottom end, one of those has to slip through the channel that it's in, and that's a little bit tedious to do. There's a bit of friction in there, and I don't really love the fact that I can't like I would basically just be pulling straight on the connections to the slip ring, and I don't love that. It feels kind of gross, and if I rip out any of those cables, there's no chance I'm going to be able to put them back in. So that would basically ruin the slip ring. So yeah, bit of an oversight, and it means that now that everything's connected up, it's extremely difficult for me to get access to anything on the inside, which is a problem. But we will talk more about that later. And yes, I'll prefer to remove the Teensy for these tests. So eventually, yeah, I figured out that I can remove the motor out of the system and just test it in isolation. And in that testing, it made me realize something that John, the aerospace engineer who's been like collaborating on this project, he warned me about this a while ago, and I didn't realize the severity of his warning when he first warned me about it. But basically, the ODrive Micro is insufficient to power the hand motor because of something that I didn't really understand about brushless DC motors, but I do now. So hey, this is learning, you know, this is good. But yeah, it's basically not, it doesn't have enough of a current limit to provide enough torque to get this to like do what I wanted to do. If I was running this, if I was running the hand motor, this little like drone motor at an extremely low torque, it would be fine, probably. But because I want like a bit of oomph out of this thing to actually throw the ball, it's not going to cut it. And to explain why, I have some numbers. So this is all calculations that I could have done in advance, but I just didn't understand that I had to. So here we are. So basically, what we can do is we can take the KV rating. Then this isn't very long as well, so don't worry too much if you're not that interested in this. We take the KV rating of the motor, which is essentially a proxy for like how fast the motor wants to spin. It's like its natural speed. If we divide 8.27, a magic number, by that KV value, we can get how many Newton meters of torque we will get per each amp that the ODrive puts out to the motor, or that the controller puts out to the motor. And this is not very much with this motor. Because the motor has such a high kV rating, it wants to spin really, really fast, but at a very low torque. And that way it can still output a fairly decent power because it's spinning so fast. But in my case, I don't really want it to be spinning like drone speed fast. I just want it to be spinning like fairly fast. I think the limit that we're getting to is like 50 revolutions per second, which I'm sure for the drone people out there is probably like absolutely nothing. Maybe, I don't know. I'd be interested to know how that fits in actually. But I definitely need like a fair bit of torque at the lower speeds. And so I don't really care so much about power, I care a lot about torque. And as it happens, the ODrive Micro has a limit of 7 amps going out to the motor. So we have this number, 5.5 times 10 to the negative 3 Newton meters per amp. If we multiply that by 7 is the peak torque that we can get out of this. The actual like operating, the continuous current that the ODrive is rated for, I think is like 3 amps. So it's actually half of this-ish. So we can only get like 40 millinewton meters out of this, which is like not much at all. Compared to the ODrive Pro, which can output a peak current of 120 amps, gives us 0.6 Newton meters. And of course, because the only thing that differs in here is the current output of the two controllers, we can very easily see that using the ODrive Pro to control this motor, we can get 17 times more torque out of the motor, which is pretty nuts. And had I run these calculations before, I would have saved myself a lot of CAD time because we can't use the micro for this, which is good to know now, I guess. Yes. So, you know, learning. Yep. Okay. We also had a problem though. So this explains why I was having a problem with this really high kV motor, because the kV is so high, the current output of the ODrive Micro is fairly low comparatively to the Pro, so we can't get much torque out. But this is a 1500 kV motor, and that's the only reason it doesn't work. We also have, on the pitch axis, this motor, which is 90 kV, which is, what is that, an order of like 20, almost 20 times less? Like, this is a very, very, very low kV comparatively, which means we should be able to get a lot more torque out of this. But last week we saw that I could get this motor to calibrate. It would like spin and do its calibration thing, but it would never actually move once I commanded it to move. And the resolution of that is that I have no idea what the problem was, and once I just changed some things around, like it worked in this isolated setup, and I was like, oh, that was easy, it just works. And then I like tuned it all up and got it all like behaving kind of nicely, and it all worked completely fine. And I tried it on the actual robot and it worked completely fine. I think the issue was something related to the fact that I'll show you on the CAD for this. I'm using the ODrive Micro's onboard encoder for the commutation encoder for this motor, which is basically what allows the drive to control the motor. It's reading like the position of the motor directly, but then like I don't really care what the position of the motor is. I more care about the position of this whole arm up here. So to measure that, we have this load encoder down here, which again, I hate that term. It's not clear at all what that means, but whatever. We have this encoder down here that measures that absolute like output angle, and that angle is also, that encoder is being read by this ODrive. And so what I'm actually commanding this ODrive to do is like move this arm to specific angles, and then it's figuring out where it needs to move the motor to in order to get that encoder to read the right thing. And I think there was just some kind of like error in how I had set that up. I don't really know. What I ended up doing was actually telling this ODrive, even in situ, that it had no load encoder at all. Like it was just using the commutation encoder and that's it. And once I got that working, I was obviously being very careful with setting my target positions and that sort of thing. Because if I had put the decimal point in the wrong spot, it's possible that this thing could have broken itself. I don't think so, but yeah, it could have happened. But once I got that working, then I tied in the load encoder stuff and it just kind of worked the first time that I tried it. So I don't really know what the problem was last week, but it's gone now, so that's good. And the next problem that I had, this is the last thing before we can see some fun stuff. I mentioned that I was seeing a lot of errors on the CAN bus, where when I had the ODrives connected up on like through the web GUI that ODrive has made, I was seeing a lot of like restarts on the CAN bus and a lot of just like errors in transmission. And I had not really any idea what was causing that. And at the time, I hadn't really done any deeper diagnosis, any deeper like testing into any of this. I had checked my termination resistors, so because that's a pretty easy check to do, and that was all fine. But I'm not really sure. Yeah, I was basically noticing errors, but I hadn't really done any looking into it yet. And similarly, that problem just went away. I don't really know what was causing it, but after I had like changed some stuff around a little bit, and yeah, once I got it all rewired again, it all just worked. So, yep, that was good. And something that's actually kind of been helpful with this is that I now have a USB CAN adapter that actually works with my Windows 10 PC. So I've been trying to find a way to basically read the CAN messages on my Windows 10 PC so that while I'm working through issues on a CAN bus, I can just plug this thing in and then see what's going over the bus. And I have tried so many of these, well, maybe not a huge number, but I've tried a couple of these devices and none of them have been working on my Windows 10 PC. But I now have one that does, and I don't know where I put it. It's on my desk here somewhere, but my desk is messy. Ah. Yes, this guy. I've put a link in the description for this as well, so if you are curious to check it out, you can. And I'll show this off in the demo in just a sec as to like what the actual UI looks like. To be honest, the UI is a bit shit, and it's very laggy, and it's not great, but it at least tells you the messages, and yeah, it kind of works. It does the job, and it actually works on my PC, which is good. Okay, enough talking. Let's see that bot move. So, I have my camera set up here, very nice. And you may have seen in the thumbnail that I have Space Mouse control working, which is very cool. So I can turn power on, and we're up. I don't know if you can hear that sound. It's kind of loud, but I'll talk about that more in a sec. And let's start my Python script. All right, so I should, yeah, where should I'll put this over here. So if I tilt forward, we tilt forward. So like the pitch of the Space Mouse is connected to the pitch of the arm, and then I can control the yaw based on speed. So whatever yaw angle I'm at, that's like setting the speed of the yaw motor. So I can angle to face you. There's a bit of lag here, so it's kind of tricky to get it directly positioned. And then we can nod. And it does work. Both axes do work at the same time, but there's a bit of sketchiness with the way that I'm sending these commands out, which I'm not worried about at all in the long term, because what I'm doing right here, right now, is I've got the Space Mouse, which is connected over via Bluetooth to Jugglebot computer, which is running Ubuntu, because that's the only way. It doesn't matter. Linux is better at connecting to external devices. Yep. So the Space Mouse is going to the Linux PC, which is then going over a USB serial connection over to the Teensy, which is then reading the, basically like we're sending out like pitch as like an angle in over serial, and also the yaw as like a speed over serial. So there's like this really shitty droppy connection of serial trying to send my commands out to the robot. So I'm pretty sure that's the only reason why the movements don't really work at the same time. Like I can't really get both to move simultaneously. It's always just like one or the other. I'm fairly sure that's to do with the serial connection, so I'm not too worried about it. But yeah, it's so good. It's so satisfying, and it's so smooth. It's such a nice system. I am a big fan of how this is coming together. But yeah, as you can probably hear, it's a little bit loud. And I think that, so in tuning this, I was having a hard time tuning the large motor, the pitch motor, so that it was quiet, because this whole thing is kind of like acting like a big resonator. And so any little tiny vibrations that are in the motor are just getting picked up by like the bass and getting resonated out. So I don't know what I can really do to fix that, but yeah, it's a little bit loud at the moment. I don't know if, let me turn up my mic and I'll bring you nice and close and see if you can hear it. Yeah, big groany, but you know, it's all right. I'm thinking that like when this is actually being used, I might have like a low power mode where it's just kind of like sitting idle and like all the motors are just kind of off. But yeah, it actually works and it's pretty awesome. I'm very, very happy with it. So I just want to show you quickly the CAN adapter output, and then I've got lots of other stuff to talk about. Alright, so I'm plugging this in now, and now I need to be careful because there were so many times when I was testing this where I had the USB-C cable connected up to the ODrive micro up here, and then I would start the yaw going, but before I had Space Mouse control set up, I was just like sending the speed commands manually, and so I would set like, yaw, move at 60% speed, and it would just start going, and then the cable was getting twisted up and twisted up and twisted up and twisted up. That was a hectic time. Yeah, so here we have this CAN interface. So yeah, this is all wired up now, so I should be able to open the COM port. And yeah, so we can see, let's clear the messages. Let me close the bus first. As I said, it's kind of laggy. It could be because I haven't restarted my computer in a little while, and maybe I need to, but at least this tells me that there are messages going over the bus. It tells me the frame IDs of them, and it tells me the data. And so I have this set in it right now so that it like overwrites existing messages. You can also set it to not do that, but then it just like fills up the thing really fast. And annoyingly, this interface doesn't tell you like how many messages with that frame ID have been received, which is a kind of useful thing to know. So yeah, I don't know. The UI is a bit shit, but the fact that it works on my PC is a big plus for me. So yeah, I don't know. If this is something that interests you, check out the link in the description. All right, I think that's it for the demo. Let's power off. Also, actually, by the way, if you are interested in how strong this is, it's pretty decent. So I'll turn it back on and go back to here. It's a little bit tricky. I don't really know how to show this because as soon as I try to lift it up, I think I might have just like cooked something. All right, hang on. Give me 1 sec. Yeah, no, all right. Let's try this very quick. For some reason, the USB connected to a different port this time. Just Linux things. There we go. All right. Yeah, so let me unplug this so I don't forget about it. And yeah, I don't want to fuck around with the yaw axis and you may have noticed that when I wobbled this before, and it actually does have a fair bit of play in it. I'm fairly certain that that play is because of my dodgy 3D printed gears, where the motor that connects to, I'll show you in the CAD. The motor that connects to the yaw motor, sorry, to the yaw axis, this guy here, only has a very small output shaft, and the little like trim, the key cutaway thing is like tiny. Like that edge there is 2.8 millimeters long. And so my 3D printed gear that sits on this, I'm fairly sure basically this has happened where like it's what's the word? Fucked up the plastic so that they're not really that like solidly attached. And yeah, I'm pretty sure that's where a lot of the backlash is coming from. But yeah, so I'm not too worried about it. I'm planning on making some better fitting gears for a future version, because this wobble is pretty intense. But as I said, I can't open this up to get in here, so I don't know exactly what's actually causing this. But yeah, as far as the strength goes, it's actually very strong. So like I'll hold it down when it tries to go up, and you can see it's like lifting up the whole thing. Like actually, maybe I can do this. Yeah, that's cool. So it's pretty decently strong. I can definitely stop it. Like, don't get me wrong, I can very easily stop it. And I actually deliberately set the torque limits on this motor to be quite low. So that way, if it does happen to run into either end, it's not going to break something trying to like continue torquing along. So it's definitely strong enough to do what I needed to do. And I have a pretty good feeling that it's going to be precise enough to angle to exactly whatever angle I want it to. So it's very cool. It actually works, and I'm kind of amazed by that. Happily amazed, no doubt. All right, let me clear up my space a little bit. Okay, what is next? So something that I've been thinking about a lot during the last couple of days while I've been getting this to move is that it's going to be fairly important that the arm knows exactly what angle it's at. Because if I have this up on the shelf and I want it to throw down to Jugglebot, it needs to know its position, which it can do. It should be able to do without too much hassle using the motion capture markers that I've got on the base here. So these will be read by the cameras, and we should be able to know the position of this pretty nicely, like the yaw angle, and also the like absolute position of the whole thing. So that shouldn't be too bad. But you may notice that I don't have any markers on the arm up here. And part of the reason for that is because I don't know if the cameras will actually see the arm all that well. And there's not really a whole lot of spots for me to put markers on there. And I don't know, I think it's unnecessary for now. And one of the more obvious spots to put markers is up on here. And that's actually the equivalent spot is where I have a couple markers for Jugglebot. But since doing that, I have realized that that's actually a really bad spot to put the markers, because this mechanism in here, both of these red parts are designed to move up and down to tension the hand string. So if I have the markers on there and I have it all set up and it's all ready to go, it's all calibrated with like where those markers are for that rigid body, then if I later down the line, the string stretches a little bit and I have to tension the string, I have to raise these two red parts up using like this screw that's in here, and that's going to move those markers, and it's going to make it, I'm going to have to like recalibrate everything. So in hindsight, that's a bit of a silly spot to put the markers, even though it's a very tempting spot to put them. So what I was thinking is that I could put so that we know exactly what angle this arm is at, one of the easiest options, the most obvious options in my mind, is to use something like an inclinometer, which is what I'm using, what I was using on actual Jugglebot to measure the orientation of the arm part. And I actually do have a second one of these. I bought two when I got the one for Jugglebot. And this is basically like a little micro electromechanical device that's in here. And as you tilt it around, there's just like a little mass held up by little tiny springs, and that mass moves around according to where gravity is, and magic happens, and we can measure the position of that mass, and that tells us what direction gravity is in very, very, very accurately. However, if we start putting sensors up here, no matter what it is, if it's this or anything else, then we're going to need to have some way to read the data from those sensors, which poses a problem because the thing doing the reading is the teensy down in the base here. That's a bit of a spoiler, isn't it? Teensy down in the base here. And we need to get the signals from the sensors up here down into the teensy. Right now, I'm doing that with the slip ring that I showed before, where I have 4 channels. I've got power, ground, CAN high, CAN low, and that allows the CAN signals to go through, which is enough for the ODrives. But if I have a sensor on here, I'm going to need to add some more lines. So I had a quick, yes, but the cables, we don't want to twist the cables. We've gone to so much effort to get this to be able to spin 360 degrees, well, infinite degrees. We're not going to add in cables now to ruin it. And so I was doing some quick thinking about this. This was actually earlier today. So if we wanted to add this exact inclinometer, this operates over SPI. So we have the 4 SPI lines as well as the 2 power lines, like 5 volts and ground. But for the power lines, we can reuse the existing 12 volts and ground lines that are coming through the slip ring already. We will need to add a buck converter, but that's fine. That's pretty easy to do. And that gives us a total of 8 channels. We'll have 12 volts ground, CAN high, CAN low, and MOSI, MISO, SOC, or clock, and chip select. Annoyingly, so I got to this point, I was like, okay, cool, let's just see if I can find a slip ring that has 8 channels. The manufacturer that sells the one that I'm currently using has 2 channels, 4 channels, 8 channels, sorry, 2, 4, 6, and 12. No 8, which is a little bit annoying. And the 12 one is a little bit bigger than the current one. And I was like, I don't need 12 channels, I only need 8, maybe this won't work. But then I realized that I actually don't think we need to add any sensor at all to this. Because even with the inclinometer on here, we still need, that's only going to measure with respect to ground, like with respect to gravity. But what we really care about is what angle does the arm need to be at, given where it currently is mounted, to be like vertical. Basically, yeah, so okay, let me start this again. The inclinometer just measures the direction for gravity, but we have another way to do that, is what I should have said before. We have a different way to measure where gravity is, and that is experimentally. So what we can do is we can do essentially, I did basically the same thing on actual Jogglebot when I was calibrating the inclinometer on Jogglebot. That's where I was going. So even if we mount this, the inclinometer, onto Ball Butler, however we mount that, it's not going to be guaranteed, because I'm going to be 3D printing the parts that do this, we're not going to be able to guarantee that it's perfectly collinear or like parallel to the aluminium extrusion, or like more specifically to the linear rail, but they should be pretty parallel. So it's probably going to have like a little bit of misalignment. So we're going to need to calibrate where the inclinometer is with respect to the actual thing that we're trying to measure. And the only way that I know of to do that is what I did on actual Jogglebot, which is to put the thing in what it thinks is vertical, throw a ball, see where the ball lands. If it's not directly on the hand, then we need to adjust something a little bit. On Jogglebot, this is easier to do because I have full like rotation freedom, but I basically like rotated it around and positioned it ever so slightly until eventually it was throwing perfectly straight up and down. And then whatever reading the inclinometer said at that point, we know that that is now 0. That is now vertical, straight up and down. And we can do basically the same thing with Ball Butler, where we don't even need the inclinometer at all. What we can do is put this put this on my desk or wherever, have it so that it thinks it's vertical, throw the ball, see where the ball ends up. This is where having the slow motion camera really helps, and also having the motion capture cameras really help, because I can track the position of the ball through time, and I can see along which axes it's tending towards. But basically, yeah, throw it up and down until eventually, like by tuning that pitch angle, eventually we will find the point where it is spot on vertical. And then we know, given where it is currently positioned on, let's say on my desk, we know that that angle is perfectly vertical with respect to gravity. But you may say, that's only fine while it's on your desk here. As soon as I move it onto something else, or if like one of my cats comes along and bumps it, or if somehow like a piece of paper wedges itself underneath, that's going to tilt the whole thing, and so that angle is no longer going to be vertical with respect to gravity. However, this is where the sneaky motion capture markers come in, because I'm yet to test this. I'm just kind of fingers crossed that this will work, but I'm thinking that once we do that calibration, let's say it's on my desk, we have it throwing so that it's going perfectly straight up and down. We know exactly what angle of this arm we need to be at to get this to be vertical and have a perfectly vertical throw. We can calibrate that with respect to the rigid body that we create in the motion capture software, and that way we always know from this point, wherever the rigid body is that's defined by these 5 markers, wherever that is, we know the angle with respect to like that local Z coordinate and the gravity, and like where the arm needs to be aligned with gravity. Hopefully that makes sense. And this means that as we move this around, we can put this at whatever angle we want. And as long as we know the offset between these 5 markers and gravity, which is another thing, but we can talk about that later. As long as we know how this rigid body is situated with respect to gravity, we therefore know exactly what this arm is doing with respect to gravity. Now, I don't currently have anything set up here that will tell me exactly what direction gravity is in. Like all of everything that's set up in here to do with the motion capture cameras is only like referencing each other. So there's no like absolute reference for where gravity is. And this was actually something that John suggested a while ago, but it hasn't really been super necessary up until now. But, well, it's still not yet, but will be soon probably. Which is this idea of having like a hanging mass somewhere in my room where I've just got like a string that hangs down, and I'll have something on the end, basically like a plumb bob, but for the motion capture cameras. So that way the cameras will be able to see this thing, and they'll say, like, it'll have like a marker up the top and a marker down the bottom and one somewhere else. And it will basically say like, wherever this line is, that's gravity. And we're taking that to be Z. For every other body in this room, that is Z, because that's gravity. And gravity is what we care about when we're juggling. Yeah. So then we can reference that with our rigid body for Ball Butler, and that will tell us what angle the arm needs to be at to be aligned with the gravity vector. So I'm pretty sure we can get away with no extra sensors. How precise this will be, we will see, but I suspect it should be pretty close enough. But we will find out in the future. Yes. Yeah, so I think that shouldn't be a problem, but I'm curious to know if you have any thoughts on it. So, big question. What to do about the hand motor? Because, as it is right now, we can't control it with the ODrive micro. And a huge part of this CAD was based around this being an ODrive micro sitting in here. It was so nice, so compact. I spent a long time trying to get these 3 parts to all like merge nicely. And it was very nice, but we can't use that anymore. So we have to go to an ODrive Pro. I have actually put in an order for ODrive S1s, which seem like the kind of in between the micro and the Pro, but they're not going to be here for a little while. And what I want to do is use what we know works. It's possible that the ODrive S1, which is a little bit smaller than the ODrive Pro, it's possible that that will also work for the hand motor, but we know that the ODrive Pro does work because that's what Jugglebot's using and that's what I've always been using when controlling this motor. But where will it go? Because it's so damn big. I've tried, so that's where the ODrive Micro is, and if you put the Pro in, boom, it's Udge. It's a chunky one. And like, it does fit in the exact same spot. So this is lined up with the onboard encoder being like the thing that's reading from the hand motor. This does work. It does fit, but like, not really. It's a bit too big for my liking. Like, it's very close to hitting some of the other stuff, and like, it's just kind of gross. It does not vibe with me at all. Well, I don't vibe with it, whichever way that goes. Not good. I don't like it. Not a fan. So I've been thinking about where else I could put this, and one option that has presented itself to me is to put it down like this. So yeah, I was originally thinking I can put the ODrive Pro somewhere, like for example, I could just like smack it on the base over here. So let's say we have, instead of it being over here, we have it over here, so that this is, come on, like this. We can have it like partially embedded into the base, and then we can use a separate encoder, just like a little encoder on here, similar to like this one that we've got here. We can basically have this encoder on the back here instead of the ODrive Micro, and then run those lines out to the ODrive Pro, and it'll be fine and easy peasy, hunky dory. But then I got to thinking, and thinking is always a bit dangerous, because I've got an idea that's potentially cool, but will be a fair bit of work. So we'll see how we go. The general idea is basically the same as what I just described for the ODrive, so we find some place in the base to hide it, and I think that this is a pretty nice spot. I will probably unsolder the screw terminals on here because that green is not doing it for me. But this spot generally fits pretty well. Like the CAN cables, I'll have to figure out some way to get them into here. I don't know exactly how that's going to work, but this is a fairly neat spot to put it. But the bigger difference that you may have noticed is the setup with the hand motor, which is very exciting, potentially. So during this whole process, I was wondering if there's any way that I could make this a little bit more neat. Because as neat as this is, and like as compact as it is, this stuff in here is like not super neat. And like it's decent, but I don't know. It could be better. And like I don't know. It could definitely be tighter. And I was thinking if something like this would work, where we basically have the string. Obviously, I haven't fixed the string CAD up properly yet. So like this string would come down, and then as it goes around these two spools or pulleys, it would go around the spool down here and then back up around the other one. Like this. So I've done a sketch here so that I can kind of guesstimate how these things would actually move. So this, we've got the aluminium extrusion is like this section in here, and then we've got the strings. Actually, maybe I'll make that a construction line so it gets less in the way. And then we have the string line is the one that goes around the outside. So that will wrap around these two pulleys and then go around the motor spool just like this, where it will cross over like that. And now you may have noticed that as this thing pitches up and down, if the hand motor stays completely still, then these strings will be wrapping and unwrapping ever so slightly from that spool, which would move the hand along the stroke a little bit. Because as, like for example, as we move clockwise, like this length of string is wrapping around the spool, which means that it's going to be pulling down, like down along here. And then the other side, this side, is unwrapping from the spool, which means it's going to be going up and extending out. So if the hand was on this side, then the hand would just slowly, ever so slightly, be moving down in like this direction. Which I'm debating whether this would be a problem or not. If it is a problem, we could always just get the hand motor to move the same amount. Like whatever pitch angle we have here, like this is something that we're measuring pretty precisely and we're like controlling pretty precisely. Whatever pitch angle that is, we can just move the hand motor by the same angle and that's going to completely cancel out this effect. I don't know how precisely the hand motor will be able to follow such small position changes, but it should be pretty close. And more importantly, I actually don't know if that's going to be a big issue. If the hand does move, like it's only going to be like less than 5 millimeters, I expect, that it will ever move down as a result of the pitch axis moving. I actually don't think that that linear offset would create any issues with throwing, because when the ball is thrown, like that event is so fast and there's such a small period where the ball is actually being thrown. Like it's such a brief instant when the ball is thrown. And because the offset is just linear, I really don't think it makes much of a difference if you throw from here or if you throw from here. Like if your peak speed is here or here, the ball's still going to go in pretty much the exact same direction. This is all like just vibes. I haven't actually done any calculations on this, and I don't really intend to be honest. I feel pretty confident in my vibes, given my juggling experience. But if anyone has any feelings otherwise, and you actually do the calculations and you realize, oh no, that 10 millimeters, or let's call it 10 millimeters, a huge difference that the hand will be offset by, prove me wrong. If you feel like it is a significant effect. I don't think it is. I think it'll be fine. However, that said, where this actually will potentially make an impact is at the limits. If we're consistently moving the hand right down to the bottom of its stroke to like get as much throwing distance as possible, then if it has moved by a couple millimeters without the hand motor realizing, then it's possible that it could run it into that end stop without being aware that it will have done that. So like at the very limits, I think this approach is a bit sketchy, but I don't think it will be that bad. Again, it's not going to be that much distance, so I don't think it's going to be a significant problem. And we can always just move the hand motor to accommodate it. So Fuzzy says, my worry would be if the hand is at maximum position, then moving could cause excess tension in the string. Yes, that is very possible. I'm still very much leaning towards having the top of the hand be like a little shock absorber thing. And I don't know exactly how the process of like loading a ball and then throwing the ball and like returning to load again. I don't know exactly how I'm going to set that up, but I don't think it would be too hard to just have it so that like either once the throw is done, hang out at the top and just chill there, in which case moving up a little bit, getting rammed up into the compression thing at the top, that's not going to be a problem. Or we can just say, okay, you've done the throw. Now, before we move either like any other axis, move the hand back down into the middle and then move the other axes. Like that's only going to be like a fraction of a second step to carry out, and it would save from this effect. Yeah. Good morning, Alice. Can't stay today. That's all right. You can watch later. Well, thank you for joining while you could. It's good to see you. Yeah, so I'm like tentatively hopeful that this could work. And there's a cherry on top, which ties back to an idea that I had a few weeks ago, which is that if we are doing this sort of approach where we have the hand motor down the bottom below the aluminium extrusion. We do, like, there are concerns around how to actually support this thing, which I'll talk about in just a sec. Well, a couple minutes. But leaving that aside, if we have this same approach where we've got the motor below the extrusion, that means that we now have a bit more freedom as to where the motor is actually mounted and how this actually works. Potentially opening up the possibility of doing what I was proposing a couple weeks ago. I actually did not prepare anything in the CAD for this. So you're going to have to, I'm just going to verbalize it and you're going to, hopefully you'll track. But basically having the hand, instead of being on this face here, we have the hand on, let's go slider. I think this should work. I always forget how the slider mates work though. Oh, there's no mate connector there. Aluminium extrusion is so good in real life. It's so shit in Onshape. It's so annoying to mate things to. All right, let's just do this. Can we get it to face the right way? I need this edge. Yes, okay. And now hopefully, yes, nice. Okay, so now imagine instead of the hand being where it actually is, like on this side, or where it currently is, we can have the hand on this side, where it slides up and down like this. Because if we turn the motor by 90 degrees, it's not going to get in the way of anything else. In the past, the reason why I couldn't do the hand like this is because there was nowhere to put the hand where it would allow for the string to be routed like up and down and around. I'm now just realizing that I do have issues with this bracket, but I feel like that bracket is movable. We can move this around and have it not be an issue. And I do also have the bolts that come through here. But again, I think that's movable. And I think it might maybe be possible to have the hand going this way, and that way we'll be able to pitch like pretty much the whole way down. The biggest thing that's stopping us from pitching down really far right now is that if I fix this, the first thing to hit is this clunky guy over here. On this side, this arm is still like a couple degrees away from the base, but this side, because it has to be so big to fit the pulleys for the string, it hits the ground first. Now, of course, in reality, if you actually like take a step back and have a look at this and like what that would mean for throwing the ball, this is probably a bit of an unrealistic position for this to be in, but maybe it would open some stuff up. I would obviously have to change the structure of the hand to be able to support the ball. I mean, actually, maybe that would stay in but in any event, having it be able to go further is not going to be a bad thing. I think it will potentially open some stuff up. And of course, if this is sideways, then this hand is never going to hit the base because it's just running up on the side. And as Fluzzy has said, it does also make the design super clean. At least having the motor down the bottom here. It doesn't, I think the cleanliness was going to be pretty similar if the motor is like this or if it's 90 degrees from where it is, as I've been describing. But yeah, I agree. This is, if we get rid of that guy, this is so clean. Look at that. It's so good. Now, of course, part of the cleanliness here is because this aluminium extrusion is basically floating right now. Which brings us to how to do this when we've got the motor running into our main support shaft in here, if I can click on it. And this is going to be a problem if the motor is facing this way or if the motor is 90 degrees from where it is now. In both cases, we're going to hit this thing, this dowel, because this dowel goes the whole way through. Now, the reason why the dowel goes the whole way through is because for the previous design, we were using that section of the dowel to support this end of like that, the lower support arm for this like side of the pitch axis. But if we change this around, we can't use that dowel for that support anymore. So basically what I'm thinking of doing is having, actually I drew this before, I'll just use the same drawing. I don't want to show you too many spoilers, so I'm going to need to copy this from something else. Actually, here we go. I can just screenshot my screenshot. That works. Does the job. All right. It's doing something like this, where I have a, the motor's coming out through here. I would obviously like cut the dowel pin to be small enough to fit inside here. And then we extend this. So rather than having the 3 pieces where we've got this support arm, and then this attachment piece, as cool as that is, and as much time as that took me to CAD, maybe we can make it a bit more simple in some regards by combining that all into one piece, where we've got just this single black piece would extend out. The aluminium extrusion would sit in there somehow on that side, and then we would also have an additional bearing support over here. So right now, the main ring, this big red ring, is only actually contacting, where it's circular edge. I've gotten rid of all my edges. There we go. It's only actually contacting these 2 bearings on the sides. So like that middle section is just kind of wasted space. I mean, we do have the channel through here, but we can move that. This middle spot, as far as the actual structure goes, is, yeah, a little bit wasted. So what we could do is move the second bearing over to be a little bit closer to this first one, and then have this third bearing, this guy here, be the support bearing for the main big support arm. And this would mean that the actual, like, the aluminium extrusion part is going to be kind of cantilevered out over like this. But I don't think that would be an issue, because this big part should be pretty damn strong. And like I can print that out of like the nylon or whatever stiffest material I have and make it like suit like lots of perimeters and everything, and I trust that that's going to be pretty solid. Is my thinking. Now, one other concern that you might have is with this setup, because the pulleys are so close to this spool here, as the string wraps around, as I've got it here, and I'm not really sure whether it would be better to have the string cross like this, or if it would be better to have the string just like come down and just like go straight, like, yeah, hopefully you get the idea. I'm not sure which way would be better for that stuff, but I can just test that out. But because these are so close together, this spool and these pulleys, as this string winds and unwinds, where's my pen? As the string winds and unwinds, so it's going to be like, and then there's like a little kind of tied off section in the middle. This is going to go up to there. This is going to go up to here. This angle in here, if that gets too steep, then the string is just going to work its way off the side of the pulley, and all hell will break loose. That's not good. If that happens, then that's a failure. That's no good at all. So we need to be careful that this angle doesn't get too steep. And of course, as these 2 axes get closer and closer together, eventually, just because we have to wind like 200 millimeters of string, the string has some thickness, and so this, I need a different color now. This distance that the string is going to spool over is a constant value. And as we decrease the distance between these 2 axes, that constant value is going to mean that this angle is going to get wider and wider and wider and wider until eventually it's going to be a problem. Whether or not this level of closeness is going to be a problem, I'm not 100% sure, but I'm pretty confident that it won't be. Because in the current design, you may have noticed that the hand spool is very close to the first pulley as well. And I mentioned this in the stream last week, that this was my biggest concern about this design that I'm showing right now. And it turns out that it's actually not a problem at all. I've completely removed it from the robot right now. Like I've gotten rid of this motor and the ODrive micro here, because as we've talked about, that stuff doesn't work. So I can't show you that right now, but it's not a problem. I manually ran it up and down the stroke many times, and there was never any sign of like the string bunching up or the string getting close to coming off of the pulley here. And these axes are 40 millimeters apart. And what I have in this CAD, very rough CAD, of course I can very easily move this aluminium extrusion up a little bit to increase that distance if I need to. But this, as it is right now, is 32 millimeters. So I don't think that 6 millimeters is going to make that big of a difference, but even if it does, we can just move the extrusion up and it's not going to be a problem. So this distance should be fine. Yep. So I'm very tempted to do this and to commit to the hand being 90 degrees from where it is, so the hand's going this way. I think that would be very cool. Yep. But we'll see how we go. That's a big CAD mission. Yep. We'll see. And then, yeah, I think that I'll keep with the ODrive Pro here. I don't really know. I don't love it. I really don't love the green screw terminal block. But yeah, we'll see how we go with that. Now, one other thing that I don't really have any solution for right now, but I'm curious to know if anyone has any thoughts on it, is that one thing that I've noticed... why did that move? What the heck? I think it's like... whatever. Go back down there. This camera just loves like spying on me when I'm not paying attention to it. Yeah, I want to give you a good shot of this because I'm kind of surprised by it. So, you may remember the very first prototype that I made of this like pitch axis thing. I've got it up here. I've had to salvage the motor from it, but yeah, this first prototype was very wobbly and like it's hard to get across on camera because the hand that's holding the thing is moving as well. But like these arms have quite a bit of play in them. That was no good. And I have been talking about how much more stiff this design is and how it's amazing and like it's really rigid thanks to the thanks to the fact that there's that single M8 dowel pin that runs through the whole thing. That makes this whole thing a lot more stiff. And also there's way more bearings and stuff in here. It's all like locked in a lot more tidily. But once it's actually in situ, it's actually got a fair bit of wobble. And I don't think this will come up very nicely on the camera, but maybe I give you a bit more light. Let's go like bright mode. And what is this? Kelvin. I really want this to be able to like auto adjust. Like if it's daytime, it will always do 5600, and if it's always nighttime, it'll always do 3200. But anyway, that's the thing for later. This is actually wobbling in the base. So like, as far as I can tell, this top mechanism is like fairly stiff. It's quite good. It's obviously not as stiff as if it was all made out of metal, but like for printed parts and for what I need, I think it's stiff enough. Honestly, even this wobble is probably not going to be an issue, but it's something that it's more than I would like to have, I think. And I'm pretty sure the problem is that like this whole lid, because it's fairly thin, like if I show you a cross section through here and let's exclude the lid. Oh, actually no, let's keep it. This whole lid is fairly thin and it's got a lot of cutouts and stuff in it. And that is the only thing that's supporting the whole top section. And that lid in and of itself is only actually connected to the bearings by these 2 bolts, as I described last week. And I believe that because of that like tenuous connection, that leads to this whole thing wobbling around a fair bit. Maybe more than I would like. I don't really know, because like nothing's going to be pushing this around when it's actually being used. So maybe it's not going to be an issue, but it is a bit wobbly. And if anyone's got any thoughts on how I can make that less wobbly, I would love to know. It's a little bit tricky though, because like the obvious answer is, given that I just mentioned that this is only connected by 2 bolts, well, what if we use more bolts? What if we use all 4? Like there are 4 bolts that connect through the the bearing. Maybe we can extend those all out to go through the lid as well. But that's going to interfere with my manufacturing process, because the reason why I only have 2 bolts fastening down the lid is because the other 2 that are in here I put in before the lid goes on to attach this gear to the bearing. And if I don't have those bolts going to the gear, then the gears, I'm going to have no way to attach the gear, because as soon as I put the lid on, I can't access the gear anymore. So I can't hold it there while I do the screws up. So it's a bit tricky, but possibly that will become a lot easier with this. What to do about poor electronics access. So you may remember at the beginning of the stream, and also like just now, I've been talking about how in hindsight, this is perhaps not the most, what's the word? Modification friendly, let's say. Because once this is together, the only way to get it apart again is to like basically pull on the slip ring cables and hope that they don't break, and hope that I can like slide them back through the channel without them ripping out of the slip ring. I'm thinking, because I'm going to have to take this apart eventually, I'm thinking that what I will do then is basically like grab the cables that come up through the bundle here and like push them down, which they are in a cable sleeve right now, so I'm gonna have to take the cable sleeve off. But basically take the cable sleeve off, grab them, push them down while I'm pulling the rest of the big ring up, And hopefully that will make those cables slip through the channel rather than ripping them out of the slip ring. So you can see like in here, that's where those cables run through. And they do go through pretty nicely. So there's not a huge amount of friction. So I'm hopeful that if I'm pushing while I'm pulling the thing up, it should come out nicely. Hopefully. But that's definitely not something I want to be doing all the time. So yeah, I need a better solution for this for the next version of when I print this all off. And this is where I perhaps went a little bit over the top with this, but I think it's going to be pretty cool. You may have noticed some new cuts in this design. And what these cuts are, we've got a hinge, print in place hinge, which should be pretty interesting. This is going to be probably my most daunting print ever, I think, this base. It's very large, and it also has like the print in place base, the print in place hinge, and like a lot of, I don't know, very weird features. And we now have as well a nice flat surface on these flanges out here. So that way, if I need to do any maintenance on this, I can just tip the whole thing back. There's a single screw in here that fastens, maybe this view, maybe might be better. Hopefully you guys like lines. There's a single screw through here that fastens the lid part onto the main part. And of course, this has to be at a 45-degree angle because this is going to be print in place. These need to print at the exact same time. I'm very curious to see how this section works out. There's not a lot of tolerance in there, but we'll see. Of course, as well, these connectors will be moving with the lid as well. That's a fairly important thing. They will be connected in here. The only reason why they don't move in the model is because there's a bit of like a circular, the way that I've mated this all together, it means that if I have these connectors mated to the moving part, and then if I have the moving part moved like down here, and then if I update that context, then it all breaks, it all falls apart. So it's just a little bit safer so that I don't accidentally do that. I already do have a couple like do not update contexts, it feels a bit dodgy, but yeah, I'm trying to avoid having too many of those. But it does mean that we have to just use our imagination that these connectors come as well. And yeah, so this is very cool. It also means that the yaw motor will be separated from the gear. So I'll be able to open it up like this, and then I'll be able to test like the yaw motor, and I mean, the other two will move their axes, but at least I'll be able to like test this stuff without having to risk like moving the whole thing around, which should make testing a bit nicer. And of course, this board will come as well. I actually, in this version, I think I have the board attached. Yeah, so the TNC is moving as well. Now, you may have a concern with this, which is that, again, we have cables coming out of the slip ring here. So there's a bunch of cables coming through here. We've got like originally I had the motor cables coming through here as well, but I won't anymore, and I'll talk about that in a sec. But we definitely have the come on, get out of here. We definitely have the slip ring cables and also the cables for this encoder down here, this green guy. So those cables will be coming out, and they have to get down onto the teensy, and we need to make sure that no cable is going to get like pinched or cut or anything as a result of this hinge. And originally I was like, oh, maybe this is actually going to be a bit of a hassle to make sure that the cables don't get pinched. But I actually don't know if it will. Because if we have a look, this is the picture of, yes, we need to open up the base. If we have a look at the picture of what the electronics currently are on the inside, here we see the bus bar stuff that I mentioned, God, like an hour ago. And we can see that actually, let me quickly go to the CAD first. What we would need to have happen to have the cables not be an issue here is we can't have cables running across from like directly from the motor to the teensy, right? Like that's a pretty obvious one, because if there's cables coming through here, they're going to get pinched when we close it up. We can have cables run around the outside here, like conveniently right where the bus bars currently are. And the main, I don't know, routing point for all the cables. I need to get rid of this stuff. This is in the way. Get out of here. The main routing point for these cables will be around the top edge around here. So if we can get all the cables to come around here, they'll obviously have like a little bit of a loop so that there's ability to like allow for this movement. But if those cables can run up around here and then connect into like one of these multi-board clips, or maybe I'll actually add that one back in that corner in there. I hadn't seen that before. But if they can run up around on either side and then run along this like bridge to the slip ring, then we shouldn't have an issue and the cables should be fine. So even when we're in the lower position, the cables should be able to just come up here, have the little loop so that they don't get pulled too tight, and then come up through, get clipped onto the multi-board clips, and then go straight into the slip ring. But that's potentially a big if as to whether or not we can get the cables to run that way. Until we have a look at how the routing actually currently is. And if you ignore the motor cables for now, all the other cables are already doing that. They're already coming up around here, up around here. They're already going in the direction that we want them to go in, except for the motor cables. So all of these ones, I might just add a bit more tolerance to them. And to be honest, I might change this white cable because this is like a PVC cable and it's like super not flexy. But if I change that to a more flexible one, like this black one is very flexy, and just had like a little bit of a strain relief tolerance bridge kind of thing, then this shouldn't be an issue at all. And to be honest, the only reason why I have the motor cables going through like this is just because I want it to be a little bit fancy and have it all be kind of neat. Like there's literally no reason why I have to have them go through like this versus just like bending them really quickly and then sending them to the motor driver, which is right here. Like these motor cables go through here. It's the blue and the yellow one. They just like come through here and then come around to the driver that's like right next to it. So there's no reason why the cables need to go that way. I don't need to do that at all. And I cannot erase. Cool. There we go. Yeah, so if these cables just come through like this, then all the other cables can stay the same, pretty much, except for like extending them out a little bit. So I think that this idea should work very, very, very well. And of course, this will give me much better access to all the internals. So I can very quickly flip the whole thing up, undo that one screw, open it up, and I've got ready access to everything. I'm considering as well, given that like the slip ring part will be more accessible, I'm considering having potentially a different way of like mounting the slip ring so that I can kind of like get to it as well. Because as it is right now, if once this is all together and like the stage 2 stuff, where's the lid? There it is. Once the lid is on top, get out of here. Once the lid is on top, we're still not going to be able to get access to the slip ring. So like if I ever need to change the slip ring, I'm going to have to go through that whole process that I just described before about like pushing the cables through the ring, and it's going to be a bit of a mess. So as it currently is, I will not be able to access the slip ring once it's all put together. And I'm considering how that could work, but I don't really have any good ideas for it. Yeah, it's kind of tricky. But if you can see something, then let me know. And also don't forget, all of this CAD is like fully open source. There's links in the description for, this week is a bit of a confusing week because I have 2 branches going on right now. I've got the main branch where we have this changes, the base change has been made on both branches, but the main branch still has the hand motor in the, like this, the hand motor is like as it currently is. And then I've got a like low hand branch, which is this one where the hand is down the bottom. And both of those links are in the description, so you can check out either of them if you want to. And yeah, have a play around with them. If you think that there's some way to get the slip ring in and out of here, then either feel free to let me know or give it a go yourself and see if you can get the CAD to work. Yeah. But even without that, I don't think that's going to be that big of an issue because I don't see why I would need to get access to the slip ring once it's in. Also, for anyone who's curious, I have increased the hole size. This is very hard to show. I've increased the hole size that the cables for the slip ring run into, so that way, hopefully, I won't need to do any more melty of my printed parts. Yes, so I'm very hopeful that this will work. I think it should be good. I'm very keen. And of course, as always, there are some silly things. One silly thing is with the hand spool printed part going through the bearing. And this probably makes no sense, but it will once I show you. So we need to go to, yes, this is the current design, and let's close up the base. Oop, let's just put him back in there. Yeah, so this is the problematic part. And The way that I assembled this all together was I had to screw in the motor first, because these 4 screws here, of which there's only one in the model, but you get the idea, those 4 screws fastened the motor to the printed part. I then fastened the ODrive on, the ODrive micro, with the outer 4 screws, which then like covers up all the motor screws. So the only way to get the motor off is to get the ODrive off as well. I then put on the spool, which was kind of hard to do because this spool sticks out and goes through that bearing. I have to like take that spool and like angle it in to like feed it in through here and then slide it back down and then screw it onto the motor, and then I can put the bearing on. But what this means is because this printed part is like sticking out and going into the bearing, this is was very annoying to remove, because I can't poke the bearing out from the backside because I didn't add enough of a hole around there. I should have in hindsight. There's no reason why this hole needs to be this small. It can definitely be like 2 or 3 millimeters radius bigger and still support the bearing just fine. But because I can't push the bearing out from this side, because I can't get in there because it's too tight, this is like stuck now. I can't pull the bearing out, because how am I going to pull the bearing? So this is basically stuck in here. And what I had to do to get this out is I basically like held this hex part with pliers and just manually rotated the motor like 1/8 of a turn at a time until eventually it had unscrewed enough to like poke the bearing out, and then I could pull it out and undo it the same way I did it up. Which is stupid. There's no reason why this printed part needs to stick out through the bearing like this. What I should have done is used something like a shoulder bolt, or like any bolt, to be honest, because I mean, a shoulder bolt would have been ideal, and had the shoulder of the bolt run through the bearing, and then had the screw part of the bolt go into the spool. That would not only strengthen the spool, because I'll be having a piece of metal in there, and that would like make it a little bit less likely to split on the layer lines, at least at that section. But it would also mean that I could actually take the thing apart, because then I would only need to undo that one bolt, take that one bolt out, and then this would be like cut here. Like this spool would be able to just slide out like towards the camera and just come out. Yeah, bit silly. Shouldn't have done it that way. I think that I did it this way because I had this kind of like in my mind from up here, where as it's currently set up, this is kind of the easiest way to do this, where I have the spool sticking out and going into these bearings. And I think I just had this idea of like, the spool goes into the bearing because I had done it here. But this is a completely different context, and different contexts need different solutions. So yeah, that was a bit stupid. So I don't know. Just be mindful that if you're ever doing like connecting spools up, just pay attention to how you might want to undo the thing. Because I think if I had thought about undoing this thoroughly, I would have realized that this is kind of like a one-way operation. Yeah, so that was a bit silly. Very hard to remove. And another silly thing is, why stick... Everyone hates micro USB. Like, if there's one thing we can all agree on, all the politics that's going on right now, we can all agree micro USB sucks compared to USB-C. So why stick with it? What I mean by this is that, unfortunately, well, for better or worse, the teensy that is down here doing the controlling is micro USB. And that's just how it is. That's just like the connector that's on the board. So, like, yeah, it is what it is. But of course, I want the teensy to be out here, or like somewhere on the inside of the base, but I want to still be able to plug into it to connect, like to be able to like reprogram the teensy. And what I got was, I think I might have put them, no, I've got one here still. I haven't been doing my organizing lately. I've still got shit out from weeks ago. What I got was nope, this is the new one. Maybe I did put it away, lol. What I got is an extender that basically takes like a male micro USB to a female micro USB. And that way I could plug in the male micro, I actually might have a photo of it. Here, yes. Yeah, we can see it in here. Oh, if we go on the camera. We have a male end of the micro USB, comes in and plugs into the teensy, and then that cable routes around and you can just see in the shadow where it pokes out, where like it connects up to the base. And on the other side of that is the female micro USB receptacle. And I think the only reason why I did this is like, oh, okay, the teensy's micro USB, I'm just going to get a micro USB extender and just extend the micro USB out and be done with it. And I didn't really think about the actual like usability of this. But what this would mean is that I would have a micro USB to reprogram the teensy, and then a USB-C to communicate with the ODrives if I ever need to. And it's pretty likely that at least during like the development of this, that I'm going to need to intermittently like connect to each of the devices on here, like the exposed ODrives on the top, and then also the Teensy down the bottom. So it's pretty likely I'm going to be connecting to all of these like in the same sitting kind of thing. And that's a bit, it's not the worst obviously, but it's a bit annoying if I have to use USB-C for the ODrives and then micro USB for the Teensy, for the like programming the base. And Batboy had a very good suggestion, which is to use a USB-C to micro USB extender, which is so obvious in hindsight. There's no reason why I should have used a micro USB to micro USB, because these exist. Like we have, and you can see in the CAD here, if you were paying attention earlier, you might have seen it, but this is now USB-C thanks to its, or you can tell by its nice ovular cutout. And that then turns into a male micro USB that plugs into the Teensy. And yeah, these exist, and they're actually like super cheap. So I've got male micro over here, and then female USB-C over here. Why didn't I do this before? So obvious. This is going to be not a huge quality of life improvement, but definitely like a semi big one. And yes, so thank you, Batboy, for suggesting that. It's, as soon as I read that, I was like, I'm an idiot. Why did I stick with micro USB? It's such a silly thing. Yeah. So yeah, big thank you for that suggestion. It's a very good one. Yep. Okay. So I've got one last thing for this week, which is that I have been running out of my motion capture markers. I only have a couple. I've got like, I think 20 big ones and 10 small ones, I'm pretty sure. And I'm already using a bunch of them on Jugglebot and Ball Butler. And I've had to, like, for example, to get the markers on Ball Butler, I've had to harvest them from my catching cone thing. And I've replaced them with these giant markers, the big ones. And like, look at how big they are. And hopefully this kind of gives you an idea of why I didn't want these markers on Ball Butler, because these are huge. They're like, these are 14 millimeters diameter and the smaller ones are 6.5 diameter. So big difference. And even on this, I don't really love this. It's just so like, bleh, so chunky. And yeah, so I've been trying to think about a way to get these markers for more cheaply, because the cheapest place that I can find them from in Australia is pretty expensive. So these are the 6.4 millimeter ones that I've got. A 10 pack is 115 bucks. These are $11 each for just a little ball. Feels a bit crazy. And I've been trying to see if I can create the same effect as these, but yeah, more cheaply. And I was doing a little bit of looking around, and I found these highly reflective 3D scanning markers. And these are used when you're scanning an object. If that object is like a car or something that doesn't have like a lot of features, it's very smooth, very reflective, these can be quite hard to scan. And so you can get a pack like this of 560 reflective markers for $12. And you can put these all over your object that you're scanning, and these will give like reference points for the scanning process. And I was like, well, I mean, if these are retroreflective for scanning, then they should be fine for motion capture as well. Of course, they're only 2D rather than like a 3D sphere, but at least they're circles, so that they've got that going for them. But yeah, I was just kind of curious as to like how well this would actually work. And so what I've done is I have got the catching cone with the giant 14 millimeter markers on it, and I also made one with these little tracking dots on them. And they're a lot smaller. And yeah, so they're in the exact same spots, but of course they're only 2D little circles rather than full-on spheres. So I want to show you what this actually looks like. So here we have the motion capture software. You can see my room. And all of these dots that you see here are things on the wall behind me. So all of those, a bunch of those balls on the wall are reflective, and also I've got like reflective tape up the top. It's quite bright, that up there. That is all coming up in here. So we can see like this one is probably the tape. That one would be the tape. I don't know what that one is. But yeah, these ones are all the balls. And if we start off, it's like what this should look like with like the actual markers is I can put this into the space. And this, I have a rigid body set up for this like layout of markers. And so this knows exactly where the catching cone is. And as long as I'm like staying within view of the cameras, I can like rotate this thing around pretty freely. It works a bit better when I'm standing like a bit more out in the room properly. But it's pretty decent. And it's getting it in most orientations. But then if we turn over to the tracking dots, if I have it facing the cameras, it will kind of get them. Like, it will get those 3, but it will never get really more than 3 because they're only 2D. So even if I'm orienting this in all the same sorts of ways, it just can't pick it up. And of course, that kind of makes sense if you think about it for a second, because these are only 2D. So like, as soon as this marker goes around the corner, it can't be seen. But because the big like spheres stick out a bit, they can be tracked a lot more broadly. So as much as I like how cheap these things are, like orders of magnitude less expensive, they don't really work as well for like generic objects. I'm definitely going to keep them around though, and I hope that I will have things in the future, like maybe for Ball Butler's base, like any flat object that I'm tracking, I think that these could work quite well. But for any like generic object that's going to be doing like full rotations, unfortunately, does not cut the cheese. So yeah, I'm back to not knowing what to do with these. So I could of course just like get these, and like they're not that expensive, but I don't know, it adds up. So yeah, if anyone's got any suggestions for how to make trackable, well, like retroreflective spheres, or buy them cheaply, like if there's just some cheaper place where I can get these from, I would love to know. But I would kind of love to have like a heap of these, like 100, just to be able to chuck them on whatever I want, like all different sizes would be so good. But that's going to cost a lot and is not really worth doing if they're going to cost this much. So, yep, not sure. Yep. Cool. Okay. There's one more thing that I meant to mention last week and didn't because I just was too frustrated with it at the time, but I've kind of, it's worn off a bit now. A couple of weeks ago, I mentioned that I bought some like very intense cabling to use for my SPI lines. And I just read that SPI is a little bit, it can be susceptible to noise. Like you can do SPI with like differential signaling, which seems like it's like the most bomber you can possibly have. But SPI without the differential signaling, it seems like it's a little bit susceptible to having noise problems. And of course, in Ball Butler's context, in like all of my contexts, I've got these like motors around that are creating a lot of electromagnetic noise. And yeah, those two things don't go together very well. So I was trying to find like what is like the most bomb-proof cabling situation that I could use for my SPI lines. And I came across, well, the solution that I ended up with is getting this stuff. Lap, whatever it is, whatever that number is, you can look it up if you're interested. And this has, well, importantly on this code actually, we've got 4, this confused me so much when I first read it, but we have 4 lots of, 4 lots of a pair of cables that have like whatever that cross section is, 0.25 or whatever. And then we also have 2 cables that are just twisted around each other that have a bigger cross section. So there's a lot of cables in here and there's lots of twisting going on. And what my plan is that if I want to have the most bomb-proof setup, I can have power and ground going over 2 of these cables. And then for each of the 4 SPI lines, each one of these 4 within this green cable has a second cable twisted around it. And I was thinking that I can take, for each of these 4, I can take its like pair, like the one that it's twisted with, connect that to ground, and that way that's like a shield. And then I can just have like MOSI, MISO, clock, chip select, whatever. And each of their pairs is connected to ground. And then that way, whatever noise is coming across this line, they should be very, very robust against that, because all of that noise is just going to be picked up by those ground twisted cables and yeah, get sent through to ground. But I didn't realize at the time how damn difficult and tedious that would be to actually physically do. And I've done it with this one cable where I've got pink, brown, blue, pink, blue, red, and green are like the 4 SPI lines. And then there's this like weird like solder business going on in here. That is the pair of each of those 4 SPI lines being soldered to the ground line of like the power line. This took a very long time to make. I don't remember, I didn't like time it or anything, but it was It was long and very tedious and like very hard to get in there and to do it all. And this cable is actually not even that flexible either. Like it's fairly stiff, and it would be difficult to route inside Ball Butler because it's just so stiff and so big. So I actually don't think I'm going to use this for this purpose right now, at least. I have no doubt that I'll find some application for it later on, but yeah, stiff cables are no good. And like, yeah, getting all of that soldering done is just too tedious. So I think I maybe could have anticipated that would be so annoying, like in advance, but I didn't, and now I've got all this cable, so I've got that for whenever I need it. Fuzzy says, I know some people make retroreflective spray paint that you can just spray on anything. I'm not sure how well that would work, but it might be worth trying to spray 3D printed spheres. That's not a bad idea. Yeah. Some people have suggested in the past, you can actually just, like, the thing that makes these things retroreflective is if you get a glass sphere and you partially embed it in like an epoxy or something, then that sphere will just like automatically, as long as it's embedded below, like, I think it's between like 40 and 60% of its like depth. Like there is a range that it has to be. Like if it's fully embedded, this won't work. And if it's just sitting on top, I don't think this will work. But because the sphere is magical, it will just like automatically send the light back to where it came from, as long as it's embedded by the right amount. And so this is like in all retroreflective stuff, it's just like little glass spheres, which is kind of amazing. But they do have to be embedded the right depth. And people were suggesting that I could just buy the glass spheres myself, put down some kind of like epoxy or something on whatever I'm trying to coat, and then like roll this through the glass spheres to kind of like coat it myself. And I think that this would probably work, potentially. It would require, I'm expecting it would require a bit of prototyping and testing out to actually get it to be a smooth process. But I feel like that could probably work quite well. But I don't love the idea of having like lots of little glass spheres, especially because however I'm attaching them, I would feel a lot less confident that those balls are going to stay in there compared to like the professionally made ones. And I don't really love the idea of little glass spheres being around in my space. I don't like, my lungs are enjoying being glass free, and yeah, I don't think I really want that to change. But spray paint, I imagine it's probably the same thing. I would definitely want to get like good PPE, and at least I would be doing that outside somewhere, where at least like the application of it. Still, they might come off, but I guess as long as I'm careful with them, maybe. Yeah, I'll have a look. I'll see if I can find some spray paint, some like retroreflective spray paint. Yeah, I did find, I remember a while ago, I found like the road marking paint that is retroreflective, but that stuff, I could only buy like a 10-liter can or something stupid, and it was like hundreds of dollars. So yeah, I'll have a look around, but if you can find some spray paint that will work for this, like in a small quantity, then let me know, because I'll be keen to pick some up to try it out. Spray paint is often used for bikes and outdoor stuff, so it's fairly durable. Yeah, okay. All right. Yeah, I'll have a look around. Thank you. Okay, yes, there should be a stream next week. I have nothing in the calendar right now. And yeah, we'll see how we go. I expect there's going to be a lot of CAD coming up. Given that all of the control stuff is working fine so far, fingers crossed, CAN is working, and like, yeah, I mean, you saw it all. Yeah, I think the next step is going to be a fair bit of CAD to get the ODrive Pro positioned so that it can control the hand motor. Well, the hand motor. And yeah, the base should be good to go. I think that this is ready to be printed, but I can't bring myself to do it just yet. I might like round out the fillets a bit more and just triple check that everything will fit nicely. Yeah, because as I've said before, I don't like creating waste, even though I've printed the base off now twice and this main ring off like 4 times, I think. I'm trying my best, but Bamboo just makes it too damn easy. It's like, oh yeah, this looks like it's mostly done. Yeah, print. And then like half an hour later, it's like, oh fuck, I don't even need this. Yep. It's coming along. We're getting there. All right, that's enough rambling. I hope you found this interesting, as always. And as always, if you have any feedback on any of this, please let me know. And yeah, I just know that there's stuff that I wanted to say that I haven't said, but that'll be for next week, I guess. Cool. All right. well, I will hopefully see you next week, and until then, have a good one.